Hi. I'm starting a new series on distributed control system over here. The insight and my experience with Yokogawa has helped me get whatever knowledge I'm trying to distribute here. Fine. So let's start off right away. Why don't I have a distributed control system? Yeah, DCS means distributed control system. So why at all have it? See, initially we had a lot of manual work going on. So people were not satisfied. They wanted to automate that work. So came the machines. Now machines also required monitoring. Somebody had to switch it on, somebody had to switch it off. They wanted to automate that too. Then came the control system, wherein you had a centralized controller which was monitoring n number of machines. This had a snag. Thing is, this was okay as long as the controlling activity was very limited. But nowadays the industries are like you have a lot of things going on. Maybe for generation of ammonia there would be one plant for nitrogen, one plant for hydrogen, one plant where the mixing occurs. Now let's say the plant where the nitrogen is being produced or recycled or whatever, it shut down or it trips down. The entire control system goes off and your entire plant goes off. Okay, that should not be allowed. So what was decided was, let's distribute the control system. Why give all the power to just one entity? Let's just distribute it. So hence came the distributed control system. In distributed control system, the units which generated the nitrogen, the unit which generated the hydrogen, and the mixing unit, all three had three independent control units. Now, if my one controller fails, it would definitely not trip off the entire plant. The other generation and mixing can happen. Of course, mixing may be not happening, because once the nitrogen gets depleted, probably you wouldn't have mixing going on. But still, certain things can move on. So that was the idea. So with distributed control system, we bought in redundancy in control, okay, and also load that was greatly reduced. Earlier with the centralized control system, one controller had to take care of all the loops. Now if the number of loops are more, obviously the load would be more, but here you have more number of controllers, you can distribute the load. So controlling became more efficient, more neat and organized. So we'll be dealing here with Yokogawa related systems for DCS. Even they have a history of DCS. I mean, they were the first people to come up with distributed control system. Now DCS, it requires a hardware unit, a software unit. Hardware in the sense there would be some controller sort of thing, and a box. Let's call it a box for now. A box would be there which does the controlling, and software. Why software? Software is required. You need to monitor this, right? Your box is there, it does the controlling. All right, I need to know what is happening. So you can bring it to a desktop, a console, whatever. Now a software is installed over there. This software would bring you the different windows which would help you to see even set values. Okay, we'll go into detail. Now let's just start off slowly. Fine. Okay, so now what are the actual when you say I have a DCS, what should it have? Let me see if I have a diagram. I apologize because they are not neat, but still I think it should serve the purpose. All right, I'm not sure if you can see this. Oh, this is pathetic. Can you see this? No, it's coming reversed, right? All right, let me try and explain this as best as I can. See, your one DCS, it will have a controlling unit. Okay, let's call it field control station. Imagine this is one box. That's it. This will does all the controlling. Okay. The box is ready now. What do you want to control? Ultimately, there would be some field parameters, right? I have an instrument. Values would come from the instrument that would go into your block. Block will do the computation. Value comes out, and it will have a positioner or a valve to which it will give the value, and it is controlling. Okay. What is it controlling? Let's say I have a pipe through which something is flowing. Okay, so I'll have one transmitter which would tell me what is the current flow rate. If I intend to control the flow rate of the liquid that is flowing, I obviously will have a transmitter which would tell me what is the current flow rate. Okay, this flow rate is transmitted to my box. My box would compute, and I would have mentioned to the box what is the desired flow rate that I want. Let's say I want to test 10 meter cube per second or whatever, 10 liters per second, something, some value I have provided it. So it will compute and tell the amount by which your valve has to open to regulate your flow, right? So that computation happens. See, the value that comes from the transmitter, it is called as your process variable or PV. The value that I give, or my desired value of flow rate, that is called the set value. Now based on these two, it compares these two. Let's say your process variable and the set variable are the same. That is, it's flowing at 10. Okay, it's flowing at 10 liters per second, and I am giving it 10 liters per second. In that case, the valve needn't open or close. It tries to see your transmitter is here, your valve is here. The valve, let it be at whatever position, but whatever position it is in, your flow is still 10 liters per second. So then should I alter this? No, I needn't alter it, right? Fine. So a computation happens at the box. See, if the valve is shut down, meaning no flow is happening. So if I want 10 liters per second, it would open it. So it's a percentage of opening that it would give to your positioner or valve. Why I have explained this in detail is most of them have got a really bad logic that your manipulated variable is actually the difference between your MV and I mean your process variable and set variable, which is not true. See, your process variable and set variable have the same units, but your manipulated variable needn't have the same units and range. Okay, it is just an